Jai Hind everyone. Today we are going to discuss insulator, overhead line insulator. Okay. So here, what is first of all, what is insulator? What is insulator? The insulation basically it interrupts the flow of current between two parts of the system. So basically it is used in overhead line between the conductor and the ground to provide the insulation between the conductors and between the conductor and the ground. Okay. So it is basically made up of porcelain. Okay. Porcelain and that have a clay, mica, and it have a cross arm like this one. These are the cross arm. Okay, and here nearby there is a power conductor that hinged with the cross arm and the tower structure. Okay. So we are using insulators in underground cable also, but here we are mainly discuss overhead line insulator, a insulator which is used for overhead transmission line, that is overhead line insulator. Okay. So it have basically three type. First one is pin type insulator. Okay. So the pin type insulator, that is old insulators, and we use it maximum voltage up to 33 kV. It can be used for only 33 kV. If we are using a pin type insulator above 33, then the cost of insulator goes very high. Okay, and it is old type insulator. So the drawback of this pin type insulator, if there is any damage of a particular disc of a pin type insulator is occurred, then we have to remove whole part of the pin type insulator. Means we cannot maintain it. We have to change that pin type insulator. If any point having any fault, then this is the main drawback of pin type insulator, and we cannot have use above the 33 kV. Okay. The next, that is most efficient and most using insulator, that is suspension type insulator. So suspension type insulator, they have it consists of a number of insulator discs, and these discs, they are in the vertical form like this one. If we are having this is a cross arm. So here it is disc 1, disc 2, disc 3, and so on. These are the discs that is used in suspension type. Means it is the collection of disc and that hinged with the cross arm, that is in vertical section. These are these connected in vertical section. These are connected vertically. So suspension type have a very advantage as compared with the pin type. The first one, if any disc of this insulator got damaged, then we have to only replace that particular disc, not whole unit. We have to replace that particular unit that got damaged. We can easily replace that disk and normal operations will goes on. Okay. The first one is that is impossible in pin type insulator. And generally we made the disk, if we are having one disk, then the variable voltage that can be only 11 kV, means 11 kV for one disk. So suppose we have to design a disk for 66 kV. We have to design the suspension disk up to 66 kV. Then we have to use 6 plus 1. 6 means plus 1 we are taking a security purpose, but we can have only 6 number of disks. So if we have the requirement of the disk, that depends on the voltage, and one disk on average that belongs to 11 kV. Okay. If we are going for 33 kV, then we need at least 3 disks. Okay. And if we are having a suspension type insulator and we want to operate it for higher voltages, then we can easily add extra disk to make that happen. Suppose we are having 66, we are having a suspension type disk that is working with 66 kV and we want it 132 kV. Then we have to add 6 more disk with existing insulator. Okay. So we don't need to create a whole 12 disk insulator. We need only to add 6 disk to make it operate for 132 kV. So that is the advantage of suspension type. Okay. Now the third one is strain type. So basically the construction of strain type is similar as construction of suspension type. The only difference is that in strain type the discs are horizontally connected. And these discs, they are used at a road crossing where tension is required. Basically it is used where tension is more. Then we go for strain type. So basically it is used at road crossing. Okay. And for two unequal size of tower, we can have strain type, and everything, the operating conditions will be same for strain and suspension type. So it is only difference is that they are connected horizontally. In strain type the discs are horizontally connected, but in suspension type the discs are vertically connected. Okay. And it is used, the strain type is used at a road crossing where unequal length of the height of the towers are there, or we can have it at a hill areas where the heights are unequal. See? Okay. The last one is, that is not much useful, but it is used for only cycle type. Cycle type, that is basically used up to 11 kV. So at distribution level we can have this cycle type insulator that have a operating condition maximum 11 kV. Now we are going to discuss, I am saying that the one disk for 11 kV, but when we are operating this insulator, then ideally it is have to 11 kV, but practically it is not happen. Means the voltage distribution over all the disk is not uniform due to the capacitance between the conductor and their cross arms, tower structure. So basically what happened, basically we are having, let's have a voltage distribution. The capacitance is formed between the metal part of the conductor, metal part of the disc and the tower structure. So due to this capacitance, the voltage distribution over all the string of suspension or strain type is not uniform. So let's see, here it is tower structure, here the capacitance formed within cross arm and the or disc, here it is this is power conductor. This is power conductor. So here the capacitance, let it be C, here MC, mutual capacitance between two discs. That's why we have written it M into C. Okay. This the capacitance between the disc and the ground, you can say it. Okay. The capacitance between the disc and the ground is C, and MC is the mutual capacitance that is formed between two discs. Okay. Here it is MC. Here it is the power conductor that is passes to this disc. So we can have, if we are having I1, current IC1, here I2, current IC2, here we can have a I3. So let the voltage, that is V1, here V2, here it is V3. The voltage V1, V2 and V3. If we are dealing with ideal condition, then V1, V2, V3, they must be equal. But in practically it is not. Due to this capacitance, the capacitance formed between the disc to disc and between the ground and the disc. So let's see what happened at this point. What is the KCL equation? That is I2 equal to I1 plus IC1. Okay. If operating frequency is omega radian per second, then what is the value of I2? That is V2 into omega MC. Okay. I equal to V into omega C. So here the capacitance is MC. I1, that is V1 into omega MC plus IC1, that is V1 into omega C. Okay. So here, as we can say that this omega is cancelled and C also cancel. Okay. So it becomes MV2 equal to M plus 1 V1. So we can have V2, that is M plus 1 V1 upon M. The value of M is greater than 1 and it is positive. So here we can see that V2 is going to be 1 plus 1 upon M into V1, and if you are seeing this equation 1 plus something, it means that the V2 is greater than V1. They are not equal. The lower voltage drop is more as compared to the upper disc. The voltage distribution, that is not uniform. Okay. Now we can see for the second here. For this second disc, Okay, here. So at this point, I3 equal to I2 plus IC2. What is I3? That is MC V3 omega MC V3, and here it is I2, that is omega MC V2 plus what is IC2, that is the combination of two voltages V1 plus V2. Okay, here it is V1 plus V2 into omega C. Okay, so omega and C, they are cancelled. MV3 equal to MV2 plus V1 plus V2. It becomes V1 plus 1 plus M V2 MV3. Okay, so V3 equals to V1 plus 1 plus M V2 divided by M. If you put from previous equation, then you can see how the V3 is going to have a larger value as comparison to the V2. So in this case, when we put, we have seen that V2, that is 1 plus M divided by M V1. So we can have replace it. Yeah, V1 equal to M V2 1 plus M. Okay, so here it is V3, that comes M V2 1 plus M plus 1 plus M V2 divided by M. Okay, so we can have, here it is V2 upon 1 plus M plus 1 plus M upon M into V2. Okay, V3, we can have V2 common, 1 upon 1 plus M plus 1 plus M divided by M. Okay, and here it is V2 M plus 1 plus M square divided by M plus 1. So you can see that V3, that is greater than V2. M plus something, 1 plus M whole square, that goes value that is greater than 1, and 1 plus something that is greater than 1. So that's why V3 is greater than V2. So as we have seen that if we are moving in the downward from cross arm to the power conductor, this is cross arm and this is power conductor, the voltage distribution goes high. We can say that the voltage nearest to the power conductor, the voltage across the disc that is nearest to the power conductor, have a larger value as comparison to the inner discs. Okay, so we are having one more thing, that is string efficiency. String efficiency, that is denoted by eta. What is the string efficiency? It is basically the voltage across insulator, yeah, operating voltage, we can say that, divided by N, that is number of disc in the insulator, into the voltage of disc nearest to power conductor. nearest to the power conductor. So as in previous case, n equals to 3, and let the total voltage, that is V equal to V1 plus V2 plus V3. The total voltage, that is V. Here we can see that the V equal to the eta equal to V divided by 3 into V3. As we have seen that V3 is greater than V2, that is greater than V1. Okay, we can see that 3V3 is greater than V. Is it clear? We can say that efficiency is not to 100%, it is almost 70 to 80%. Okay, so if we are doing some grading to the disk, then we can have 100% efficiency, or nearly 100%, like 90, 95, 98. But in general, without grading, we can have only 70 to 80% efficiency. Okay. So basically, these insulators we are using at a transmission level, distribution level, and ultra high, extra high. Okay, suppose we are having operating voltage that is 440 kV, then how much number of strings required? That is 440 divided by 11, 40 kV, 40 number of 40 number of strings are required. Number of string disk are required. So we can have this. Okay, let's stop the overhead line insulator.